In section 8, we're going to look at using exponential and logarithmic functions. It's really going to go back to the ideas that we learned about in section 7 when we dealt with base e and the natural log. So first thing that we're going to look at are two functions. We have two of them. One is considered the exponential growth. That's the one on the left. And the one on the right would be exponential decay. The only difference between the two is your rate for exponential decay is negative. So if you have a positive growth or a positive rate, then you have a growth. If you have a negative rate, then you have a decay. These should look somewhat familiar. We talked about compounding continuous interest, and that formula looked like A equaling something like this, where P was our initial value, E was just a number, our base, R was our rate, and T was time. And it's basically the same thing as these ones down here. A is your initial value, E is your base, K is your rate now, and T is time. So they're pretty much the same thing that we've done from section 7 to now. We're actually going to start with exponential decay. So a problem that we can look at. The half-life of radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. The half-life of carbon-14 is 5,730 years. Determine the value of K and the equation of decay for carbon-14. Okay, so understanding this idea of half-life. Think of, I'm giving you 100% of something. And I want to know how long does it take for that something to get to 50%. That's what I'm asking you to do in terms of half-life. I'm asking you to get down from an original substance, 100% of it, all the way down to 50% of it. And since we're using a decay, I want to use this function, the one with the negative exponent. Okay, so we're going to write out a whole bunch of stuff. We're going to say, I need a y, I need an a, I need a k, and a t. We're going to solve for one of those. Probably the easiest one to see is they give me t, 5,730. Okay, and it also wants me to determine the value of k. So that's actually the one that I'm solving for, which means then that I should know an a value and I should know a y value. The interesting thing is that you can choose any value you want for a and then pick y that goes with it. Since I want to know the half-life of it, I want to know how long does it take to get from the whole thing down to half of its life. So I'm just going to choose my a value to be 1, and that half of 1 would be just a half. If I chose a to be 2, then y would be 1. If I chose a to be 4, then y would be 2, okay, because I want to get down to half of its life. Once I have this information, we can just plug it in. So I'm going to say y is a half equal to 1e to the negative k times 5,730. Now 1 times anything, that doesn't do anything for me, so I'm just going to get rid of it, and then I'm going to do some rearranging up here in the exponent because we really don't write this like negative k times a number. So I'm going to rearrange a little bit to get me a half equals e to the negative 5,730 k. And then if you remember from section 7, remember to pull that exponent down. We're going to use a log to pull it down. And since our base is e, we're going to say let's take the natural log of a half, and that should equal negative 5,730 k natural log of E. We dealt with this a lot in the last section, but the natural log of E was just a value of 1. You can plug that into your calculator to check that. So 1 times anything doesn't do anything. And then to get K by itself, I'm going to divide both sides by negative 5,730. So now I have natural log of a half over negative 5,730 equals my rate. I'm going to plug this in with you guys because I think it's going to give it to you in scientific notation. So plugging this in, I have natural log of a half, I'm just going to use 0.5, divided by negative 5,730. Yep, it did. So I'm going to say let's go with stating just 1.2. We'll go with K as 1.2 for this. Notice how it had e to the negative 4 over here. That's scientific notation. So that's saying that I need to move 4 decimal places to the left. So I'm going to go 1, 2, 3, 4, fill in some zeros. My actual rate that we're going to need is 0.00012 is my rate, K. They also wanted me to take that and then write the equation. So if I write the equation, we're going to say we have y equals whatever a is. We'll just use a. I'll just keep it as a. E to the, since I'm decaying, I need a negative exponent, 0.00012 t. There's your equation. There's your rate.